Hi everyone, and welcome to your next video on Introduction to Electronics. So this one's going to be about resistors, a couple here, these things, and yeah, this is going to be your first electronic component that we're going to be covering on, losing my bits, on yeah, your Introduction to Electronics, your first electronic component. So then, don't know where we're going to go with this, got loads to cover. Resistors is a big subject. And yeah, let's make a start. So then, first up, what is a resistor? Well, a resistor is an electronic component that resists the flow of current. Yeah, that's it. That's its primary use. They're very small, they're very cheap, and they're very easy to use. Now, you might be saying to yourself, what's the point of using an electronic component to resist the flow of current when in the last video you said, you know, you can use wire to resist the flow of current. If wire does the job, then what's the point in using a resistor? Well, this is the problem. I have here, in terms of wire, right here, in terms of wire and resistance, I've got about a 200 ohm resistor, and you can probably already see the problem. It's very heavy, it's very big, it's bulky, it's completely useless to use that as a resistor. So we stick to wire for doing all of our circuit connections because it has a very low resistance, and we use resistors as our resistance. And just as a comparison, I've got a resistor here and I've got another type of resistor here. They both do the same function. I'll sit them both there. They're practically lost compared to all the wire. So that's the main reason. Small and easy to use. Second reason, resistors come in predefined values. Brilliant for us. It means that we don't have to arse about working out our resistance and measuring out wire and picking wire widths and diameters and whatever, and messing about with all that stuff in order to get, say, I don't know, 10 ohms of resistance. All that we have to do in terms of resistors, go out and pick a 10 ohm value resistor. Job done. If you want a 12 ohm or 100 ohm or a million ohms, a mega ohm, yeah, just pick it out, and that's the size it's going to be. Very small. But they do go smaller. You can get surface mount, which can be a tenth of the size of that, a millionth the size of that, even less, even smaller. So yeah, it's really a no-brainer. Resistors are here and resistors are staying. And that's what we use to resist the flow of current. So that's basically it. Now then, you can get, well no, we won't go on to that just yet. Let's go over this. How do resistors resist? If we need all this amount of wire to resist the flow of current to, I don't know, so well, that's 200 ohms to resist the current, let's say down to, you need 200 ohms to get a current flow of 1 milliamp, let's say. Highly unlikely, but that might be the case. How does a resistor do that in such a small package? Well, it's not a million miles away from that, because if I take this and a big hammer, I'll show you what's inside it. And here we have it. This is our resistor. Don't know if you can see that particularly clearly. Okay, let's try on that side. Let's brush some of this dust off it. Okay, what we have here, I'll come out of the shop, it might focus on that a little bit better, is wire. This is a wire wound resistor, and basically it's just a coil of wire that has been wrapped around a ceramic body, so it's no different from using wire before. It's just that all that we've done is So we've got a wire wrapping going all the way around here, and if I break this, try and shatter this a bit more. No, come on. Don't want a bloody break today. Ow. There we go, right then. There we go, so this is our resistor, and as you can see, it's just a length of wire wrapped around a ceramic body. Ow, bloody hammered my thumb. Anyways, yeah, so resistors, resistance of wire and resistors themselves are very similar. The only difference is that this wire is nickel chromium, I believe. If not, I'll flash it up on the video. If I made a mistake there, I'll have to look it up, but my head's screaming nickel chromium. And yeah, that's all that it is. It's just wound around a little former to make the resistance. So how do we go smaller, even smaller? Well, this is a metal film resistor. Basically all that this is exactly the same as this, except instead of wire on the ceramic body, you've got a bit of metal film that's wrapped around this metal body that provides, you know, almost zero resistance because it's just a bit of conductive material connecting A to B. But what we do with that metal film is we etch it into a spiral and turn it essentially into a spiral of wire going down the resistor. Only very, very small. So we do it even smaller. Simple. And again, you can go down a step further to a single strip of wire that's very thinly made, and you got an even higher resistance in an even smaller package. So that's all resistors are. It's not a million miles away from what we've already covered in the previous video for resistance. So then, moving on a step, where do we go from here? Yeah, so let's go into some of the characteristics of a resistor, and then we'll start looking at, you know, symbology and stuff like that. So a resistor, okay, like one of these, a fixed resistor, well in actual fact all resistors, say if we take this one, they come in predefined values of, say, let's call it 100 ohms, and on a piece of paper you would denote that as 100 ohms. Yeah, pretty straightforward. Take that into the real world, 100 ohm resistor isn't a 100 ohm resistor. It has something called tolerance. Tolerance is how well the resistor's been made, and it's a quantified amount. Okay, it has a set value to it. And in terms of resistances and tolerance in general, it's given a percentage of that particular value. So if it's said that the tolerance is plus or minus 10% of 100 ohms, then in the real world your resistor value, your 100 ohms, is going to be somewhere between 90 ohms and 110 ohms, because 10% of 100 is 10, so minus 10 plus 10 of 100. So whenever you pick out, you know, say a ton of these resistors, you go out and buy them, not many of them will be 100 ohms, but they'll be around that 100 ohm mark. So you can think of it as a measure of how well they're made. So if you make a resistor very, very, very cheaply, okay, you're going to have a very high tolerance. So the further away you get from that 100 ohm mark, more chance of you not actually getting one. And if you have a tolerance that's really tight, very close to this, so 1 ohm or points of an ohm, if it's 1 ohm, then it'll be plus or minus. You know, if it's 1% of 100 ohms, it's 1 ohm. 99 ohms to 101 ohms, so you know, it gets it closer, but because it's more accurately made, more expensive it's going to be. So generally speaking, we always go for, say, if you want cheap crappy ones, 5% tolerance. You know, 5 ohms in 100, is pretty close. Try and go for the 1%ers, they're just as cheap as the 5% value resistors, and they're a hell of a lot more accurate. Metal films like this is a metal film resistor, ones with a blue bottom, are generally 1%ers. Light blue ones are generally that little bit more accurate. The carbon film ones, normally anywhere from 2% and up. Okay, generally 5%ers, the carbon film ones. So that's tolerance. It's basically how well it's made. Next characteristic, power, the important one. That determines really whether you get carbon film, metal film, wire wounds, thick films and things like that, because power rating is basically how much power your resistor can withstand, or how much it can power in terms of heat it can get rid of before you start setting these on fire. And it's very easy to do that if you don't pay attention to your power ratings. So when a electric current flows through a resistor, it drops a potential voltage. You get a potential voltage across it, it builds up, just like I mentioned before in the previous video, in terms of resistance and wire. And when it's in the circuit, as you get that current flowing through, you get that voltage across it, it heats up. It's, you know, it's a bit like you going to the gym. The more you work out, the more harder you have to work. In other words, for a resistor, the more current that it passes, the hotter you get. Well, it's the same thing, the hotter the resistor gets. It has to dissipate that power. Too much power through a resistor, like I said, set it on fire. Too little, you know, perfectly fine. You can handle it. It's like you can lift a very light weight 1,000,000 times, so you can only lift a heavy weight once. Yeah, same problem, same effects. That power, and power rating is the maximum that it can take. That one is about 0.25 watts it can take. So when you're working out the power for resistors, okay, how much current is flowing through it, and the resistor, and using the resistance of a resistor, you can work out how much power it's going to dump. And yeah, and you pick your resistor with a power rating higher than the actual power that it's actually going to, you know, express into the world as heat. So that's basically power. So the more power and the more heat that your resistor has to dissipate, the larger your resistor has to be, which is why we got the large wire wound ones, like those, or like those, the wire wound ones. This one is known as a CERMET. So some people call it a cement resistor. Basically, it's a resistor encased in a block of cement, really, a block of ceramic, and that ceramic is there to absorb the heat, so you can pump more heat. You can get more heat out of your resistor. You can heat up more. Other types like this is another wire wound one, which is the bare wire, really, just coated, and I think you can just about see the windings on that. Maybe not. Who knows? And yeah, that's the one without. So it's not gonna handle the heat as well. And you can get loads of other resistors. Okay, they're all flashing up here. Bigger the resistor, bigger the power rating, the more it can handle. It's the rule of thumb. Okay, and when you calculate your resistors, which we'll do later on, we'll pick out resistors and we'll choose one. We'll choose the tolerance, we'll choose the power rating, we'll choose the resistance. We'll go search through the catalogues and show you. You don't have to worry about which one you pick, because all your workings out will take you basically to a particular type of resistor. So then, that's really resistors, you know, what they are. So in terms of a circuit, let's move on to the symbology, the units, and how they're expressed. And yeah, so then move over. Up here we've got the symbol of a resistor. This is the rectangular symbol. This is the one that we use nowadays, but some of you out there in the world may not recognize this as a resistor. Should do, because there are in actual fact two different symbols, and this is the other symbol, the zigzaggy line. This is the older symbol that we used to use in the UK, but we're standardised now on a rectangular one. But you know, internet everywhere, World Wide Web and whatnot, circuits around the world, you need to know both symbols, because you've got old data, you've got new data, you've got data from different countries, and you've got both symbols populating all your documentation. Most of the time it's the new one, it's the rectangular one, the zigzaggy line, it's going out. It's donkey's years old. The zigzaggy line used to represent the windings of a wire-wound resistor, because they were the de facto standard when resistors first came out. But now we're using different materials, okay, thick film, thin films, so you know, we generally do it as a square block just to represent, yeah, we've got a lump or something there and it has resistance. So the rectangular block has become the de facto standard. When you come to writing out your resistor value, adding it to your symbol, there's two ways of doing it. Either you can write down the value, which will be something like 100 ohms or 100 R, because you can drop the ohm symbol for the R value, or you can express it as, say, an R value, say R and then a number like R1, R2, R3, R4, R5, and then in a table below your circuit diagram or to the next or in a component list, you'd say R1 equals 100 ohms, R2 equals 1 kilo ohms or 1000 ohms, or you know, R3 is a mega ohm, and so on. So generally we use the R values in circuit diagrams, especially if it is a very densely populated circuit diagram, because having the value written on there, you know, it can be obscured. It's tiny little writing and you may not be able to see it very clearly, easily make mistakes, so you generally use the R values. Next thing, tolerancing is always done in percentages. It's a plus or minus value on resistors. We'll go into a little bit more about how they're coded and whatever later on when we do colour codes and ASCII codes and stuff like that for resistors. But just to say it's there and it's a percentage. 1 minute. Bloody PPI scams. Keep on bloody blasting me with tons of shit on my mobile. Right then. So yeah, so tolerancing is generally a percentage. So it'll be a plus or minus a number and a percentage, and that's your tolerance value. Normally a capital T or something like that. It's denoted as, normally in circuit diagrams it's not shown. It's up to you to pick out. You have a particular value of resistor, and yeah, it's down to you which one that you pick. Closer the better. Again. Next up, power rating. Power denoted as it always is, capital P. Power measured in watts. It's in watts. Okay, and yeah. Whenever you look through the catalogues, you will see power ratings given next to resistor codes and what have you. So you know, yeah, this lot of resistors are 12 watt resistors, these lot of resistors are points of a watt resistor, and so on. That's that done. When it expressed on a resistor itself, it isn't in generally. A lot of resistors it is left off, so you have to go by rule of thumb and try and gauge what wattage it is. If you're putting it out of a bag of mixed components, you know, you have to say, right, well that's a big chunky resistor, yeah, it will do about 2-3 watts, and that's something that you have to get used to by actually handling the components. By doing that, you get used to the sizes and what have you, and how much heat they can dissipate. Problems, so yeah, it can be a problem when it's a mixed bag. But you know, when you're going out and buying a component fresh, it's always stated and guaranteed that's what it is when you get it. So try not to mix them up. Yeah, so that's more or less it. The only other thing that you have to worry about with resistors for now, that I'll run over now before we go off into the next video where we'll start using them in circuits, show you how to connect them up into a circuit, so on, and use them in various configurations, you know, series, parallel, and we'll go over colour codings as well and the ASCII codings. I'm just going to speak to you about temperature coefficient, because a lot of the time it's left out, just like power. power ratings of resistors, if ever you learn about resistors, it's always left out. It's always left to the last minute, and it's only glanced over, but it's really important. Temperature coefficient, not so important, especially from hobbyist point of view, unless you're dealing with thermistors, which we'll get on later on as well. I'll tell you about those. They're a different form of resistor, can resist the resistance changes with heat. But yeah, temperature coefficient is basically your resistor gets hot or your resistor gets too cold, the resistance can vary. So your 100 ohm resistor might vary very slightly with heat. Good experiment for that is using a light bulb. As the light bulb heats up, its resistance is going to change a lot because your tungsten filament changes in size. As your resistor gets hot, if it's a metal or wire or anything like that, metal film, wire film, carbon film, it's going to expand and contract with heat. It will do that if you start running your resistor very close to its power rating, because it's trying to get rid of heat, so it's going to heat up. That's going to vary your resistance, and the resistance can go down, which means more current flows, which means power goes up, which means your resistor gets even hotter, which means it expands more, and eventually it'll burn out. So you have to make sure that you do run your resistor a little bit away from the maximum power rating so that doesn't happen. But it can also have the opposite effect as well, where your resistor increases with heat, and that can be used as a safety margin. So if you have too much current flowing through your circuit, your resistor value increases because of the temperature coefficient. As resistance value increases, naturally current goes down, therefore power goes down, and the resistor cools down. So you can use it to control currents that might be running out of control. Temperature coefficient for fixed resistors like these ones are pretty tight, you know. It's parts per million of an ohm. So it may be 0.0000001 ohm of 100 ohms. If it gets close, if it increases by 20 or 30 degrees above room temperature. So unless your system is really critical, so like you're doing deep sea exploration or outer space or in the middle of a desert or in a tropical jungle somewhere, or points of an ohm, points of points as it were of an ohm, it's not really going to make that much difference. Resistors are quite stable. Wire wound ones, that used to be a real pig with when they first came out, because wire expands, it's a metal with heat. But yeah, since we moved over to thick film or thin films and using different materials like carbon, silicons and other compositions and bimetals and what have you, the temperature coefficients can be quite tight now, and they don't stray very far from your resistor value unless you're really pushing them to the max and you're using your resistor as a heating element, a bit like in a 3D printer print head, where it gets super hot in order to melt your plastic filament. That's the only time when you really need to have to worry about temperature coefficients. So not really going to go much further now. This is just a basic introduction, just to show you what a resistor is, what's inside a resistor, and what they do. We're going to get down to the really nitty-gritty stuff of circuitry in the next video. We'll do resistors in series, we'll do resistors in parallel, we'll whack one in the circuit, we'll have a bash at looking up one in a catalogue, and if we've got time, again, like I said, we'll run through the resistor colour codings and the ASCII, not ASCII, alphanumeric coding. Been saying ASCII all this time, you bloody tit. Right, yeah. So we'll do the alphanumeric coding, where you use numbers and letters to denote your resistor value. We use colour coding to denote your resistor values, and we'll yeah, we'll start to, after that, we'll start to mix in maybe variable resistors and your sense resistors like thermistor and your LDRs and what have you, and we'll go even further on. And at some point I will say, alright, stop this, we'll move on to the next component. So, see you next time.